So the last talk in the session of the conference, and this is the memory management and analysis session, is StarMalloc, verifying a modern hardened memory allocator. It'll be given by Antonin, is that right?
Yes.
It's on Reitz from Inria.
Yes. So hi everyone, thanks for the introduction. So indeed, I'm going to present StarMalloc, and I would like to lay the emphasis on the fact that this is joint work with Aymeric Fromherz, who's here, and Jonathan Protzenko. So to start, I will give some context. Why do actually hardened memory allocators matter? We know that there is a large amount of commonly used software that is still written in memory and safe languages, and this is unlikely to change anytime soon. We also know that hardened memory allocators can provide a line of defense against memory corruption issues such as double freeze or buffer overflows. But these memory allocators are actually complex pieces of software, and as such, they can have their own implementation bugs. And we're going to, so this justifies, from our point of view, the need for verified implementation that meets end user needs, including performance and security. And during this journey, we faced a few challenges. The first one is that we need to relate metadata and memory space. That is, we want our metadata to remain consistent with what memory space actually is available, and we need to express the corresponding tight invariant. Also, we want to have efficient data structures, and such as double linked lists, but we don't have any dynamic memory allocation to implement them, because we're currently implementing dynamic memory allocation. Also, this is quite some low-level stuff, so we need to interact with the operating system, and for this, we need to model syscalls. Of course, this is a modern allocator, so we want to support concurrency. And last but not least, the result should be easy to extend. For example, when we want to implement new security mechanisms, which is why we developed a dedicated verification methodology that relies on composable abstraction layers. Our contributions are the following. We developed StarMalloc, that is the first verified general-purpose user space memory allocator that is hardened and usable in real-world software, such as the Firefox browser. We also get a verification theorem that states that StarMalloc is functionally correct, and we developed a dedicated verification methodology that enabled this work. Out of scope are the underlying memory allocator design and any corresponding security theorem. So now let's have a quick look at what our verification guarantees are. The theorem that we get is that StarMalloc is functionally correct with respect to a translation of the C standard requirements, assuming this soundness of the verification toolchain. And this verification toolchain is actually used in other large verification projects. To be a bit more clear, functionally correct means here that StarMalloc behaves actually like a reasonable memory allocator. And as StarMalloc is implemented using a concurrent separation logic, we get at the corollary that it is memory safe and thread safe. And now let's have a look at a more practical example. Let's look at the malloc specification. And so if pointer is the return pointer, of course, our specification accounts for the fact that this pointer can be null. And if it's not null, then it points to an allocation that is of at least the requested size. The client program will have total ownership on the corresponding array. The allocation will be 16 bytes aligned for some reason. And if the zeroing security mechanism is enabled, then this allocation will be initially filled with zeros. So now, let's have a look at StarMalloc architecture from a high-level perspective in order to justify our methodology. So StarMalloc is heavily inspired from an already existing memory allocator, that is Hardened malloc, which is a security-focused general-purpose memory allocator. And as many allocators, StarMalloc actually distinguishes between two different types of allocation, small allocations and large allocations, based on some thresholds that is actually here, the system page size. And these two allocators actually have different implementations and have also different challenges. And today we're going to focus on small allocations. So let's say that there is some client program that is requesting 24 bytes of memory. This is a small allocation, and we're going to go through the different hierarchical layers. So the first thing with small allocations is that they are grouped by size in so-called size classes. For example, in the 16-byte size class, all allocations are 16 bytes long. The same applies for the 32-byte size class that we're going here to select because 24 bytes cannot fit on 16 bytes. And actually, a size class is composed out of a large number of pages, of system pages. This number is statically known and fixed. And to return some memory to the end user, we first need to select some page in which there is some free space. So here, let's assume that we know how to do that. At the next hierarchical layer, actually a page is composed out of chunks of memory that all have the same size. And here we are inside the 32 bytes size class, so all of these slots are actually 32 bytes long. And we need to select one that is free. And at this point, we can safely return the corresponding pointer to the user. And as you see, there are many different hierarchical layers, and we want to reason about these different layers in an independent manner, and such as the verification can be modular and everything composes well. So far, you may have noticed that I've not been talking about metadata, and that this is because the StarMalloc implementation stores metadata about the allocation region and other different regions. And this is true both for metadata about slots inside one page, but this is also true for pages inside one size allocation region. And you may want to think about these data structures as arrays. That is, it will be nice if we could reason about these as sequences, but these are actually complex data structures. For example, the slots metadata actually is implemented using a bitmap, while the pages metadata is actually implemented using a viewable list, which is a really complex data structure that we'll see later. So now let's dive in the heart of our work, that is verification methodology. So we use FStar, that is a proof-oriented programming language that is used as a verification framework which supports user-defined tactics and semi-automated verification using an SMT solver. And still is a higher-order concurrent separation logic that is embedded within FStar. And its key feature is that it combines tactics and SMT rezoning for verification. And actually, let's be a bit more precise. The key feature of still is that memory shape and memory content proof obligations are discharged separately. And so let's have a look at a swap textbook example. First two lines are as expected. Next two lines specify the memory shape at the beginning and at the end of the execution of the function. Here we got two valid references that are disjoint. And this actually corresponds to proof obligations that are discharged through a custom decision procedure that is implemented as a tactic. While this actually specifies the memory contents at the beginning of the execution of the function and at the end of the execution of the function. And the corresponding proof obligations are discharged semi-automatically using an SMT solver. Now let's have a look at the VRLS data structure. That is a really complex data structure. So we know that inside our size class there is a known number of pages that is statically known and fixed. So we can think of the pages metadata as an array that is of the same length, that is statically known and fixed. And when we want to allocate, we will want to find a page that is not full. And the first approach to do that will be to say, okay, let's keep a pointer to the first page that is not full. And that will work, but at some point this page is going to be full too, so we may want to keep a pointer to the next page that is not full. And this actually corresponds to a linked list data structure inside the array. So let's sum it up. We've got a few different composable abstraction layers. The first one is we got some higher ownership that is specified using separation logic. And we can view the content of this array as a sequence. And we need to refine over the sequence of cells using a predicate that is pure and that will actually specify the list structure within this array. And this gets us to have a list view over the content of the array, and we really want to enforce that all of the pages living inside the corresponding list are respecting some same predicate. Here, all of the pages that are belonging to the not full list are actually not full. And actually, things are a lot more complicated because we want also to keep track of the full pages for some reason, and we only need to add the corresponding predicate for the list contents. But things are even more complicated because let's say that we're deallocating some allocations that is part of a page that is full. This page is going to be not full anymore, and using classical linked list, it will be way too inefficient. So we need to have a double linked list. And we can do that only by modifying the list structure predicate without touching anything else. And actually, we also want to keep track of, we also want to distinguish between partial pages and empty pages for possible fragmentation issues, so we need to add the corresponding predicates and list content. So far, I've been describing an allocator that is indeed working, but what about security mechanism? Because this is a hardened memory allocator. And actually, we also want to have another double linked list for guard pages. Guard pages are unmapped pages that are inserted inside the pages that are part of the size class allocation region. And they are used to mitigate possible buffer overflows. Let's do the same for quarantine pages. So the idea behind quarantine is that when you allocate a lot in some pages, you may want to let them cool off a bit, and we are just going to delay any possible allocation inside these pages. So this corresponds to an additional list, and actually this is even a bit more complicated because the quarantine pages are forming a queue, and we need again to refine the list structure within the array. And so what this shows is that we've been able to verify a really complex data structure using our methodology, and actually this is quite great because there are even more invariants, that is, the lists are actually forming a partition of the array. So this was one complex data structure, but of course there are many of them, and there are also many hierarchical layers, and we want to relate them using combinators. So let's have a look at some basic examples. That is an indirect pointer that is pointing to some pointer that is itself pointing to some value. And we can implement this using the SLDEP combinator, and you can think of it as basically the dependent star, that is the dependent pair for some separation logic predicates. And actually, combinators are really useful, and we use higher order combinators that can be instantiated with arbitrary separation logic predicates. And this can be useful because then they are quite generic and can be used at each hierarchical layer. And I want to lay the emphasis on the fact that these combinators are user-defined, and they are not trusted. And custom combinators are indeed defined and are used as part of StarMalloc. There are actually many other included features. We support concurrency, and this requires from us to have locks and the corresponding extraction handling. There is a mismatch between the semantics of locks that use addresses and still semantics for locks that use values. So we need to do this. We support arenas to reduce mutex contention. We also support many security mechanisms. And we support something that we really want to support, that is configurability. That is, we are able to disable, enable, or tweak security mechanisms, or even change the size classes set. And what's interesting with our approach is that we can change the configuration without modifying any proof at compile time. And there are, of course, more details inside the paper. So now let's have a look at the experimental evaluation. What we get is that StarMalloc works as a malloc drop-in replacement for real-world applications such as Redis, Lean, and Firefox. And this actually required us to implement many fun stuff, such as realloc, line alloc, malloc usable size. And we also get the following result, that is that StarMalloc gets quite good performance using the fantastic mymalloc benchmarking suite, and we actually get that verified code is on par with unverified code. And this required us to have a lot of fine-tuning and precise optimizations. I really want to lay the emphasis on the fact that this was a huge last-mile effort from us to get something that is realistic and usable. And what this gets us is, so actually StarMalloc is composed out of more than 42,000 lines of verified code with at least a third of libraries, and it gets us to more than 6,000 lines of extracted C code. To conclude, our contributions are the following. StarMalloc is a first verified general-purpose hardened user space memory allocator that is usable on real-world workloads. We developed a verification methodology that enabled this work, building upon Steele's methodology. And we get a performance that is comparable to that of hardened malloc, whose design was used as a basis. And everything is available online, and I would like to thank you for your attention.
Questions?
Thank you. What do you do in the case of malloc zero size?
For malloc usable size?
You know that you can actually
For zeros.
malloc zero. What happens?
So, so there are many fun cases. For example, for the so for malloc of zero size, I think we return a null pointer. This actually could be configurable because sometimes it's interesting to return some specific pointers to unmapped regions.
Because malloc 0 is actually not defined by the ISO-C semantic. You actually have to.
That's right, as many other things. For example, the 16 bytes alignment requirement is actually not a C standard requirement, but some hardware requirement.
Thanks.
Other questions? I had a question. Were there challenges or opportunities that were specific to verifying a hardened allocator versus a regular allocator?
So there are two things that really interested us. The first one was to have something that was configurable in terms of security mechanisms and has to support many security mechanisms. The other one was that it seems perhaps easier to specify what is the ownership on allocations using a hardened memo allocator, because once you introduce such things as caches, things get quite tricky to specify what is actually the ownership from the allocator side and what memory space actually is available.
So it's easier in some sense. I'm not saying it was easy, but it was easier in some sense, or it was more tractable because it was a hardened allocator.
So,
or perhaps because you were developing it also made it easier, or could you give more insight into that?
Sorry, I did not get it.
Oh, also because, I mean, you made modifications to the allocator to make it easier to verify as well, perhaps?
So we made very few changes, yes, and yeah, I wouldn't say it was easier, but it was perhaps easier to reason about when we wanted to specify what guarantees do we get.
Okay, hi. Thank you, great talk. I have two questions concerning the verification methodology. So if I well understood, you are doing automatic verification using SMT solver. So what are the logics, I mean theories that you are using to deal with all these levels of array and so on? And the second one is you say that you generated the C code by a refinement process or by directly? I mean, your compiler is also verified?
So there are many things that could not fit inside a 15-minute talk, but the first one is that so we rely on the still separation logic. So as to what exactly the logic is, I think it's better to use it's better to read the ICFP paper, but it's only semi-automatic. That is, we need to prove many invariants also manually, even though the SMT and the tactic helps a lot. And for example, we need to prove semi-automatically both that the memory shape is correct, and for sometimes we need some specific lemmas to do that. And also sometimes we need to just have some dedicated proof effort as to what the SMT query is at, because it's only semi-automatic, it's not fully automated. And as to the extraction process, there was actually a big toolchain that is relying on the Caramel software that is also in use for the Hacklestar cryptographic library stuff. So we go from F-star and still files to verified files to C file. And then, of course, there is some C compiler.
Any last questions? All right, thank you all. Thank you all for the great questions during the session. Thanks to the volunteers and thanks to the speakers.